So this is the second part of the notes, which you'll finish them off, and we'll talk about the classification of matter. There are two types of matter. There are pure substances, and there are mixtures. Now those can be subdivided into two further categories, and you can use the matter flow chart to help you decide what kind of matter is it. Okay? So the first thing we have to ask ourselves is, can it be, we come to the matter, and we say, can it be separated physically? And by physically, I mean, can it go through a physical change? Not can I literally, like, pick out pieces of it, okay? That sometimes people get caught up in, like, the exact words. But if I put it through a physical change, for instance, if I have salt and water, if I boil the water off, I would separate it by the physical change of boiling water, because the salt would stay behind and the water would evaporate. So if it can be separated by physical means, we come over here and we say it's a mixture, okay? And then we have to ask ourselves, is the mixture that is it uniform in composition? Meaning, does it look the same throughout? I can't visibly distinguish its parts. For instance, the said salt water we just talked about. So if I got a glass of water and I put salt in it, and I stirred it up and dissolved it, would it look the same throughout?
Yes.
Yes, so it'd be uniform in composition. So then we would come over here and say, okay, it is a homogeneous or homogeneous, however you prefer to say it, mixture, which we will also call solutions. So anytime I say something's a solution, it's also a homogeneous mixture. It means the same thing. If I look at it, let's say it's a bowl of chicken noodle soup. Can I visibly distinguish the parts of chicken noodle soup? Yes, I have noodles, I have carrots, I have chicken, maybe some broth, unless you boiled it dry. So that is not uniform in composition, so we would call that a heterogeneous mixture. Okay? Within heterogeneous mixture, you also can have colloids and suspensions. Not everything that's a heterogeneous mixture is a colloid or suspension, especially if it's not in a liquid, and we'll talk about that further as we talk about each one of these. So if I have the matter, got a new set of matter, and I say, can I separate it by physical means? Let's say I have sodium chloride, just plain old sodium chloride. Can I separate that by physical means? If the answer is no, then I have a pure substance. And I go over here, and I say, okay, I have a pure substance. Can I decompose it chemically? Sodium chloride.
So take sodium and chloride.
Yeah, can I break it back apart by chemical means to get to sodium and chloride? And yes, I can, so that means it's a compound. If I had, say, copper wire, can I, through a chemical change, break copper wire down into anything further? Nope, then copper wire would be an element. So that's how you go through that. So when you're doing this classification, you kind of have to ask yourself these questions, okay? You don't have to get out the matter flow chart and go, you can keep it up here in your brains, okay? So let's talk about pure substances first. Pure substances, by their very nature, are homogeneous in their appearance, meaning they're uniform, but a homogeneous mixture is a solution, okay? Meaning it's not a pure substance. So you got to know the difference. So by its very nature, copper wire, no matter what, copper is going to look the same, right? Pretty much anything, not pretty much, everything on the periodic table is an element. An element is composed of identical atoms that cannot be decomposed by a chemical change, and they retain their properties. Okay, so an atom is the smallest amount that will retain its properties. Once I start taking off electrons and all that, then it doesn't retain its properties. So, hydrogen, helium, copper, aluminum, iron, titanium, those are all examples of elements. Okay? Today is my favorite element day. It's the 23rd. Today's vanadium day. It's my favorite element. You want to know why it's my favorite element?
I do.
Because my first name starts with a V. Vanadium is V. It's in period 4. I was born in the month of April, and my birthday's on the 23rd.
And period 4 is your favorite class.
Nope, it's not in period 5. That is group 5.
And period 4 is your favorite class.
So what
This is
about
period 5.
5?
It is?
Yeah. So it's in period 4. I was born in April, so 4. It is the 23rd element, and I was born on the 23rd. And my name starts with V. So, I mean, it's like, what else would be my favorite element? I don't know. Okay.
Does it look cool?
It's kind of metally looking. It's a transition metal. It's like silvery. Compounds. Compounds are the second type of pure substance. They are composed of 2 or more elements in a fixed ratio. and they can only be decomposed by a chemical change. For instance, water, if I pass an electric current through water, then it will break back into hydrogen and oxygen gas, okay? The other thing is their properties of the compounds are very different from the individual elements themselves. And so if it's a compound, it's going to have a chemical formula. So here are two everyday examples, and that is table salt, which is NaCl, and table sugar, which is C12H22O11. Glucose is not the same thing. Glucose is a type of sugar. It's the type that plants are producing when they go through photosynthesis, but it is a different formula. It's C6H12O6, which y'all should probably know that from the photosynthesis equation. Yeah. So when I say that the properties are different than their individual elements, I want to give you an example, and I'm going to use salt as an example. So individually, sodium, when it's in its natural elemental form, is a soft silvery metal, so soft that you can cut it with a knife, and it's highly reactive with water and air. And by highly reactive, I mean when it hits water, it kind of blow up, burst into flames. So that would not be good in your body as just the element, because what are you made of? Water and air, right? Got some air in there too. Chlorine by itself is a green, very harsh-smelling gas. Okay, if you breathe it in, it can kill you. So individually, you would not want to consume them, but together in sodium chloride form, they taste wonderfully delicious on your French fries, right? And actually, you need some sodium in your body, but when they say you need sodium, they're talking about in its ion form, which we'll get to later in the year when we talk about ions. There are two laws that govern compounds.
Which one?
You're on the video now, Twan. The law of definite composition, which states that a given compound always contains the same number of fixed ratios of elements. For example, water, no matter where it's found on Earth, will always be 2 hydrogen, 1 oxygen atoms, H2O. Okay? So that's what the law of definite composition means. The law of multiple proportions says that elements can combine in different ratios. So basically, there's more than one way that some elements can go together. Okay? If it's a metal and a nonmetal, there's only one way they can go together. But nonmetals, two nonmetals joining together, they can actually do a couple of different things. Okay? So plants are taking CO2, right, to go through photosynthesis. Okay? What's another compound that you can think of that's got carbon and oxygen in it that's actually detrimental if you were to breathe it?
Carbon monoxide.
Carbon monoxide. Okay? So carbon and oxygen have the ability to form either CO or CO2. Okay? But when they do form those, they would be in a definite composition each time. It's a definite composition for CO, and it's a different definite composition for CO2. But they do have the ability to form multiple compounds. Nitrogen and oxygen, as you can see on the picture, they can form 5 things. That's not even counting their ions. Okay? So that brings us to mixtures. Mixtures are considered to be matter that can be separated physically. In other words, I could distill it, take the boiling points and separate them that way, could filter it. I could physically separate them out little by little. And then there's 2 types. Notice when you're looking at the particle view for heterogeneous, it's just kind of whatever. It's not anything uniform. But if you look at the one that's homogeneous, it's red, green, red, green, red, green. It's very structured and homogeneous throughout. So homogeneous mixtures are what we call solutions. And almost always we'll call them a solution, but they are homogeneous mixtures. They have a uniform composition. They look the same throughout. And although they can vary from sample to sample, each sample itself would be uniform in composition. And an example of that was, how many of you like sweet tea? Okay? How many of you like really, really sweet tea? Okay? How many of you just like your tea a little bit sweet? Okay? So those are all examples of solutions, because sweet tea is a solution. but the more sugar you have in it, you have a stronger concentration of sugar. So it's still a solution, but your solution would differ from someone else's solution. Does that make sense? So it's not like the law of definite composition that says if you have water, you always have H2O, and that's it. 2 hydrogens, 1 oxygen. Okay? But if you have solutions, you can vary from sample to sample, but the sample itself would be uniform in composition. Okay? Contact solution is an example. Gatorade. Brass is an example of a metal solution. And we call metal solutions alloys, A-L-L-O-Y. The reason someone was confused by this earlier, and like, why is that not a compound? Brass is a mixture of copper and zinc. And they wanted to know, okay, it's copper and zinc. Both of those have formulas, right? Cu and Zn. Why is that not considered to be a compound? And it's because they're not chemically combined. I could separate brass and into zinc and copper by using their melting points, because they have different melting points. So I could find whichever one is the lower melting point, and I could reach that first, and the zinc would melt out, or the copper would melt out before the other thing. So they can be separated by physical means, so they are a mixture, in this case a solution. Bronze is another example of a alloy. Stainless steel, things like that. Okay? Within heterogeneous mixtures, remember we said you could have 2 kinds. Now, not every heterogeneous mixture is going to have the colloid or suspension category in there, but they are 2 subcategories of that. Colloids are when you have a particle intermediate in size. So it's basically kind of between solutions and suspensions. The particles do not settle out. They do have the Tyndall effect, which means they will scatter light if a beam is passed through the mixture. And I'm fixing to show you a picture about that and explain that. Okay? So there's some examples of some colloids. We got shaving cream, jello, gelatin, and fog are 3 good examples of colloids. Paint is another example of colloid.
Could you go back?
I can go back.
It doesn't line, the blanks don't line up, I don't think. Or am I on the wrong spot?
No, I don't have one.
Yeah, I don't know.
Yeah.
Okay, can I look at it after I'm done with it? Yeah, I'll look at it and see which one it is. Which one are you on right now?
This one, the colloids
And what does it say?
one. Colloids mixture blank, or does blank have a blank composition?
I think we
Colloids
skipped
is below
the
it.
slide.
Did I?
There was a slide for these notes, but not that.
Okay. I'll catch that at the end and see what it is, yeah.
Yes, ma'am.
Okay, so the Tyndall effect is when you pass a beam of light through a solution or a colloid. Because sometimes a colloid can mimic a solution, and if you're just looking at it, you may not know. For instance, gelatin looks kind of the same throughout unless you put some fruit in there. But you can check to see if something's a solution or a colloid by passing a beam of light through it. So in the first picture, you don't see the beam of light traveling through it. That makes it a solution. Okay. The second one is a colloid, and you can actually see the beam of light shining through it, so that it scatters the light. So an everyday example of this is when you're driving at night, your air is all around us right now, and it is a solution. It's uniform in composition. So if you're driving at night and it's a clear night, can you see the beam of your headlights from your car pass through the air? No, you can't. You can see where they hit on the ground. You know they're on. They're illuminating stuff, but you don't actually see them traveling through the air. But if it is a foggy night or a foggy morning, can you see that beam of light?
Yeah.
Yes, you can. Matter of fact, if you put your high beams on, it scatters it back to you, and you have trouble seeing. So fog is, in fact, a colloid. And what it is it's just water molecules that are just suspended. Yeah. Okay. Mixtures that are suspensions have particles in a solvent that are so large that they settle out unless the mixture is constantly stirred. So Italian salad dressing is one of the best examples of a suspension. Yes?
On here it has the colloids definition twice and no suspensions definition.
Yeah, I don't have that one.
Oh, so it's a mistake on my notes.
Yes.
Okay. So we'll get that fixed. Okay.
So should we write this?
Write suspensions and yeah. Yeah, I redid the notes at the end of the last year, and I didn't catch that before I sent them to print. So that tells us how, y'all are the first people to say that today. This is fifth period. You would have thought first and second would have said. There was one little girl that came up and said, I didn't get something right on the notes. Is it going to be on Canvas? Well, so it's a good thing I didn't record earlier, because now we can correct anybody watching that colloids is accidentally in there, you said twice.
Yes.
So the second colloids, let's take it out and put suspensions, which have particles that are so large that they settle out, unless they're constantly stirred or agitated, which means shake it up. Okay? But you all know that Italian salad dressing, oil and vinegar, so the oil's at the top, vinegar's at the bottom. If you shake it up, it'll stay mixed for a second, put it on your salad, but then whenever you let it sit for a while, it re-separates. And we don't talk about the Tyndall effect with them because obviously, would it show the beam of light? Well, if I was trying the muddy water, could I even see the light? Probably not. Yeah. So other examples of heterogeneous mixtures that may or may not be considered a suspension, like if you have the M&Ms there, those would probably not be a suspension. They're just a heterogeneous mixture. We said earlier chicken noodle soup, what would that be? It would be a suspension because you've got your, although, do the noodles actually stay suspended or do they fall to the bottom of the bowl?
You can still separate it.
Yeah.
Separates.
Yeah, but yeah. So that's right. So if you stir it up, it stays, and then, yeah. So,
It would
all right.
be a suspension.
Yeah. Normally, we just ask you to do homogeneous or heterogeneous. I might give you a few examples of colloids and suspensions. But there's a big difference between, if I say heterogeneous mixture and then I tell you shaving cream is one and chicken noodle soup is one, obviously you know there's a big difference between the way they look. And so the shaving cream one might throw you off a little bit unless I give you the categories of colloids. Yeah. Yes?
So is heterogeneous mixture the same thing as a colloid?
A colloid is a subcategory of a heterogeneous mixture. A colloid
Okay,
is
got
a
it.
heterogeneous mixture. A suspension is a heterogeneous mixture. It's just a subcategory. It's like further classification. Yes, sir.
How would the Tyndall effect work with shaving cream?
Well, it wouldn't really work with shaving cream. And really and truly, the only time you're going to use that Tyndall effect is if you are trying to determine, I've got this unknown stuff in this jar or whatever. I need to know, is it a colloid or a suspension? Okay, so then I would do that. But shaving cream, I know is not you know what I mean?
Right.
Yeah. Okay. Now, I'm going to pause the video because y'all have some drawing to do. And I don't want the people watching the video to have to wait for y'all to draw. But they should pause the video right now, and they should draw these particles. So the last thing that we'll do is just practice labeling. Okay, how about sand? What would sand be? What type of matter? What kind of mixture? Hetero or homogeneous? Hetero. Sand, if you pick up a scoop of sand, it does not look all the same way. So it's heterogeneous. It's got different color pieces in there. Because what is sand actually made of?
Rocks. You said glass.
All I could think of was heating.
It's
Sand makes
sand,
Oh, I
yeah,
thought they were.
or, yeah.
That's what I was thinking.
Oh.
Okay. What about antimony?
That's a compound.
No, it's an element, yeah. It's number 51, SB. So it's an element. If it's an element, that makes it a pure substance. Okay, how about table salt, NaCl, compound? If it has a formula, right, it's a compound, which is a pure substance. We'll say PS for that. How about salt water? Maybe a homogeneous mixture, or we can sometimes call that a solution. And we're discussing like salt water, which is just salt and water. If I got a scoop of salt water from the ocean, would that be homogeneous?
No, there's gross stuff.
There's gross stuff in there, yeah.
Wait, so it's homogeneous because if you like looked at it, there would be salt
Yeah.
in the water, like that.
So yeah, like if I just took salt and dissolved it in water, now it's a solution. Yeah. How about brass? Homogeneous. That one should be easy. We just talked about that, right? Homogeneous solution, mixture. Aluminum, an element. How about a burrito?
Hetero.
Heterogeneous mixture, yeah. And how about glucose? Compound, because it has a formula, right? Whoops. Let me rewrite that. It got a little messy. Okay? Any questions at this point? All right.